The coldest places in the universe are not where winter lives. They are not hidden in the shadow of distant planets or buried beneath alien ice. The lowest temperatures ever found exist in silence, between stars, inside the dark emptiness where light itself becomes rare. There, heat drains away into the endless night, and atoms slow until they almost forget how to move. Tonight, we drift toward one of those places, the coldest natural temperature ever discovered in space. A quiet region where matter freezes not because of snow, but because the universe itself refuses to keep it warm. Before we begin, if this calm journey brings you even a moment of stillness, a gentle like or a quiet tap on subscribe would mean more than you know. Your presence here is already a gift, one that keeps these quiet stories alive. Now, let us drift into the first chapter of this frozen wonder. Part 1. How cold can the universe become? Cold is not the absence of warmth. It is the slowing of motion. Every atom vibrates, every particle jitters. Temperature is simply the measure of how alive that motion remains, and somewhere in the deep starless void, that motion quiets, almost to nothing. When you step outside on a winter night and the air brushes against your skin like crystal, the cold you feel is still filled with motion. Molecules of oxygen and nitrogen rush across your face, vibrating with energy. Your breath forms clouds because the warmth within you meets the dancing particles outside. Even the iciest wind on Earth contains energy rushing through its atoms. True cold, the kind that the cosmos holds, is far beyond anything we can touch here. To imagine the coldest places in the universe, you have to imagine stillness. Not silence as we know it, but a deeper kind of silence, one that lives inside atoms themselves. For heat is a kind of motion. When things warm, atoms shake faster. When things cool, they slow. And if you could keep cooling, keep draining energy away, you would eventually reach a point called absolute zero, 273, 15 degrees Celsius, or 409.67 degrees Fahrenheit, theoretical perfection, the moment when motion stops entirely. But nature resists perfection. Even in the most vacant stretches of space, the laws of physics refuse to allow atoms to become perfectly still. Quantum mechanics, the fundamental rules that govern the microscopic world, say that particles must always have a tiny flicker of motion, a hum too soft to ever fade away. Scientists call this zero-point energy. It is a minimum heartbeat of existence. Still, the universe tries to come close. As you drift farther from stars and planets, warmth becomes rare. Light grows thin. Radiation, the sun's invisible gift of energy, fails to stretch across the distance. Heat evaporates into the cosmic background, the faint afterglow of the Big Bang, and the universe settles to a temperature just a hair above absolute zero, about 2.7 degrees Kelvin, cold enough for atoms to cling tightly together, cold enough for time, in some sense, to slow. And yet, there are places colder than that. Imagine a spaceship coasting far from the Milky Way, its engines long silent. There would be no wind, no sound, no radiation strong enough to keep motion alive. The craft would chill to near the cosmic temperature and then slowly toward something lower, a temperature determined not by heat, but by emptiness. This is the strange truth. Vacuum is the greatest refrigerator ever built. When matter drifts into space, it gives up its heat into the infinite dark. There is nothing to trap warmth, no air to press energy back into atoms. It leaks outward endlessly. Space does not cool objects aggressively, the way wind strips warmth from your skin. Instead, it quietly absorbs every stray spark that escapes until there's almost nothing left. But almost. Not everything. Because even here, far from stars, the universe carries a faint glow of microwave light, the leftover light of creation. It washes through everything, a silent thermal bath that prevents any region from reaching true zero. Without this relic radiation, the cosmos would be even colder. But even so, some places manage to sink below the average temperature of the universe itself. How does that happen? Cooling, in its simplest form, is expansion. When gas spreads out, its particles collide less often, losing energy to empty space. On Earth, when you spray compressed air from a can, the metal chills instantly. Expansion steals heat fast. Now scale that up to the cosmos. When stars die, they often cast off gas into enormous clouds that race outward faster than heat can follow. In some rare cases, this expansion cools gas clouds to temperatures colder than the cosmic background itself. Colder than the universe. It sounds impossible. How can something be colder than the temperature of space? But temperature doesn't care about averages. It only cares about motion. A gas that stretches outward too quickly is like a dancer leaping into the darkness. Energy left behind, motion slowed, motion quieted. These are the regions where the universe's deep freeze becomes real, places where atoms drift into a state of near silence. Even the simple act of shadow can produce colder worlds. On the moon, sunlight roasts the ground to 120 degrees Celsius by day. But inside deep craters that never see the sun, places of permanent night, temperatures sink below 240 degrees Celsius, nearly the lowest that physics will allow naturally. These shadowed basins are some of the coldest places we've ever recorded in the solar system. And yet the moon, even in darkness, is not the coldest place nature can craft. To reach the very bottom of the cosmic thermometer, we must look not to planets, but to emptiness. The spaces between galaxies, the hollows between stars, the regions where heat has no source and no refuge. Here, the universe reveals its quiet truth. Warmth is rare, and cold is the universe's natural resting state. As stars age, they slowly lose their energy. The nuclear fire within them dims. White dwarfs, the remnants of once brilliant suns, cool over billions of years until they become black dwarfs, frozen spheres of matter in a darkness unimaginable. The universe has not existed long enough for any star to reach this state fully, but the future promises a night where even starlight fades into memory. So the question presses quietly into the mind. What happens to time in this cold? When particles hardly move, when energy lies silent inside atoms, time seems to stretch, not because clocks run differently, but because change itself becomes hesitant. Chemistry slows, reactions pause, lifetimes of stars and galaxies stretch outward as the cosmos relaxes into entropy. Cold is patience written into physics. Even today, in this relatively young universe, the vast majority of space is closer to absolute zero than to the warmth we know. We live in rare pockets of heat, bubbles inflated by stars and atmospheres. But beyond the glimmer of our sun, beyond the bright arms of galaxies, lies a temperature so low that numbers hardly capture it. A temperature measured not by feeling, but by the absence of feeling. Cold is the universe's default. Warmth is the exception, the rare spark we call a star, a planet, a living breath. Life thrives in defiance of the universe's desire for stillness. We exist in a narrow range where motion remains lively enough to build complexity, but slow enough to remain stable. A slender comfort zone between fire and frost. As you breathe right now, heat radiates gently from your skin into the air. If you were unshielded in space, that heat would leave you too, drifting outward until it joined the background glow of ancient light. The same destiny awaits every atom, every star, every wandering world. Cold is not destruction. It is the quiet end of motion. It is the universe's calmest truth. And yet, even in this quiet truth, a deeper question remains. If the universe is always cooling, is there a place where it becomes as cold as physics will ever allow? As we drift deeper into this story, one frozen wonder captures that question perfectly. A place where cold surpasses even the universe's natural chill, where a dying star creates the coldest known temperature in space. That is where our journey continues next. Part 2. Cosmic Background Frost, the universe's default chill. After the Big Bang's fire dimmed, the universe settled into a silent coolness. All around you, even now, a faint relic glow fills space at just 2.7 degrees above absolute zero. It is the temperature of ancient light, a cosmic winter that never ends. This subtle cold is woven into the very fabric of the cosmos. It is not the chill of wind or ice, nor a darkness that bites the skin. It is a quiet temperature spread evenly through the entire universe, the cooled echo of creation itself. When the Big Bang first erupted, temperatures were beyond imagining. Everything we know, matter, light, the laws of physics, existed in a storm of energy hotter than any star that will ever shine. But expansion began. And with expansion came the inevitable truth of thermodynamics. Heat spreads, motion slows, and fire becomes frost. As the universe stretched outward, its light stretched with it. Photons that once burned with fierce power were pulled thinner, weaker, colder. This is called cosmic redshift, a gentle lengthening of light waves as space expands. Over billions of years, that once searing radiation has faded into a soft background microwave glow. Instead of warming worlds, it barely nudges atoms into motion. Tonight, that ancient glow passes silently through you. Unseen, unfelt, yet constant, a thermal fingerprint left over from the universe's birth. Scientists call it the cosmic microwave background, or CMB. It surrounds every star, every galaxy, every breath you take. If you turned off all lights in the universe, if every star flickered out and every planet cooled to a silent rock, the CMB would remain, bathing everything in its quiet chill. When astronomers first discovered it in 1965, purely by accident, the universe changed forever. Two scientists at Bell Labs were trying to eliminate radio noise from their antenna. No matter what they cleaned or tested, a faint hiss remained. That hiss wasn't from Earth at all. It was the whisper of the Big Bang, a fossil of energy older than galaxies, older than atoms, older than time as we know it. From that moment on, humanity had proof. The universe had a beginning, and that beginning had cooled into something we could measure. If you could tune a radio to the right frequency, you would hear it, a faint static like winter static on an old television screen. What you would really be hearing is the glow of 13.8 billion years of cooling. The CMB is astonishingly precise. Across the entire sky, its temperature barely changes, only by millionths of a degree. But within those tiny ripples lies the blueprint of everything. Those are the seeds from which galaxies grew, the silent scaffolding that shaped the cosmos. Slightly warmer regions held a bit more energy. Slightly colder regions held a bit more matter. And as time passed, gravity gathered those seeds into stars, planets, and eventually you. Imagine a map of the universe just after its birth, not drawn in ink, but in temperature. A map where warmth and coldness mark the first structure of everything. This is what satellites like COBE, WMAP, and Planck have revealed, a universe whose frozen background is rich with history. ESA's Planck mission, with its astonishing sensitivity, produced the most detailed map of the CMB ever made. It showed us that the universe is incredibly flat and uniform, but not perfectly so. Those imperfections are the reason galaxies exist. If the CMB were flawless, matter would never have gathered. The universe would have remained a thin, endless mist, so even cold carries purpose. Think of how strange this is. Every moment of warmth in the cosmos exists only as a rebellion against this default temperature. Stars fight back against the cold. Life clings to warmth like a fragile ember. And yet, in the spaces between, the frost returns. The CMB defines the baseline of existence. It is the lowest natural temperature that anything can fall toward, unless physics gives it a special reason to cool further. Planetary shadows, gas expanding from dying stars, and unusual pockets of isolation can dip even lower. But the CMB is the universal floor, the background cold waiting patiently beneath every spark. In a way, the universe is a fading fire. Expansion continues, and expansion brings cooling. As space stretches further, the CMB grows even colder, its photons more diluted, more redshifted, more silent. In the distant future, its temperature will drift so close to absolute zero that even measuring it will become nearly impossible. Stars will vanish, black holes will evaporate, galaxies will separate into darkness, and through it all, that ancient light will keep cooling, gradually surrendering its energy to the emptiness it expands into. The CMB is often described as the universe's baby picture, a snapshot of a time when everything was still molten possibility. But in truth, it is also a portrait of the universe's eventual fate. We look at the past and glimpse the future, a cosmos that continues to cool toward stillness. Right now, here on Earth, surrounded by warmth and motion, it's difficult to appreciate how cold space truly is. You are wrapped in an atmosphere, basked in constant sunlight, and heated from beneath by a molten core. The universe protects you from its true nature. But leave this cradle even briefly. Step away from the warmth of a star and temperature. Crashes rapidly toward that cosmic background minimum. Cold on the largest scale is the rule. Warmth is the exception. And yet, despite its simplicity, the CMB holds mysteries. Subtle asymmetries in its temperature, a strange alignment in the sky called the axis of evil, hint that the universe may not be perfectly random. There may be a preferred direction, a memory embedded in the frost of ancient light, of something deeper, a twist in the first motion, a quiet spin of the cosmos that physics has not yet fully explained. The CMB asks questions even as it answers them. It tells us that the cosmos began hot and chaotic. It tells us that expansion cools everything inevitably. It tells us that cold is not emptiness, but history, a timeline written in microwave wavelengths. Tonight, as you rest, that ancient glow passes through you, billions of photons per second, little messengers from the universe's first moments. They do not disturb you, you do not feel them. But they are there always, marking the temperature that lies beneath creation. The CMB is the universe's quietest story, a reminder that every burst of starfire, every living heartbeat, every warm moment exists against a background of eternal cold. And as we continue this journey into the frozen depths of space, one question grows even sharper. If the universe is filled with this quiet frost, how can anything become colder than the background itself? In the next part, we drift toward a dying star, a place where motion slows past the cosmic limit, where cold beats the universe at its own game. Part 3. The Boomerang Nebula, a natural cryogenic miracle. In a distant star's dying breath lies the coldest known natural region in space, the Boomerang Nebula. Its gas expands so quickly that warmth cannot keep up, leaving a temperature colder than the background of the universe itself. Colder than the universe. That phrase feels impossible. How could any place fall below the frost of the cosmic background, the 2.7 Kelvin chill left behind by the Big Bang? And yet, 5,000 light-years from Earth, in the faint constellation of Centaurus, a dying star has pulled off that quiet miracle. Here, in this ghostly nebula, the temperature reaches just 1 Kelvin above absolute zero. 272 degrees Celsius, 458 degrees Fahrenheit, a cold so deep that motion nearly halts and heat has nowhere left to hide. If you could drift toward this nebula, the journey would feel quiet and strange. No freezing wind would greet you, because wind needs air, and space holds almost none. The cold here does not strike like winter. It simply erases motion. Atoms lose their energy not quickly, not painfully, but slowly, quietly, inevitably. At the heart of the Boomerang Nebula lies a star like our Sun nearing the end of its life. Once bright, once stable, it has entered a stage astronomers call the pre-planetary nebula phase. Its nuclear fuel is fading, its once orderly layers begin to loosen. With nothing left to hold them in, the star's outer atmosphere races outward at astonishing speeds, nearly 600,000 kilometers per hour. This is where the cold is born. When gas expands, it cools. You feel this every time you breathe out slowly, the warmth of your lungs turning cool when it meets open air. Now imagine that common sensation rewritten onto a cosmic scale. A star losing its outer layers. Gas expanding into the emptiness of space with such speed that heat cannot cling to it. Energy is carried outward and lost to the void. The gas chills faster than the universe can warm it. The Boomerang Nebula is cooling through expansion so dramatically that even the constant haze of microwave radiation filling all of space is not enough to stop its fall toward stillness. It is nature's own cryogenic chamber. No human technology could ever cool as efficiently as this dying sun. The name Boomerang Nebula is a poetic misunderstanding. Early images from ground-based telescopes revealed a shape resembling a thrown boomerang, two arcs curving gracefully outward from the star. Later, sharper views from the Hubble Space Telescope showed something different, a nearly perfect bipolar cloud, like a bow tie woven from starlight and shadow. But the name remained. Sometimes science keeps the poetry even when the picture changes. The nebula glows faintly, lit only by the light of its fading central star, a star still hidden behind thick, frigid gas and dust. It has cast off more material in a short time than our sun will shed in millions of years. Astronomers believe this rapid loss is temporary, a brief and violent exhale in a star's slow death. Inside that cold, chemistry changes. Molecules drift through what might be the closest the universe has ever come to absolute zero. Collisions between atoms occur rarely, not because they avoid each other, but because they simply do not move fast enough to meet. Reactions pause. Time itself feels stretched. The invisibility of warmth reveals a different kind of structure. Delicate threads of gas, silent flows shaped by gravity and magnetic fields. In such an extreme cold, dust grains can cling together, icy particles forming seeds of what may one day become planets, though not around this star whose time is quietly running out. Cold here is not destruction, it is transformation. For astronomers, the Boomerang Nebula is a laboratory the universe built for us, a place where the rules of heating and cooling are pushed to their limits. By studying its light, by observing how certain molecules absorb and emit radiation, scientists can trace the temperature with precision. Even the faintest photon carries information about the motion of the particles it touches. And the message is always the same. Motion is slowing here. The nebula is coasting toward stillness. But it will not remain the coldest place forever. In the future, the star at its heart will heat again, gently, gradually, as it transforms into a white dwarf. The icy winds will calm. The expanding gas will begin to glow more brightly, bathed once more in starlight. The Boomerang Nebula will warm. Its record-breaking cold will soften into something more ordinary by cosmic standards. This miracle is temporary, a moment captured in the life of a star just as it transitions from fire to quiet. There is a haunting beauty in that impermanence, a reminder that even the coldest silence is part of a motion that never truly stops. Stars live, stars fade, stars release everything they once held tight, making space for new cycles, new worlds, new warmth. Right now, this nebula is one of the universe's greatest extremes, an oasis of cold in a cosmos that continues to fall in temperature with every passing epoch. But someday, far ahead, long after its central star becomes a white dwarf, too cool to ignite anything new, the Boomerang Nebula will join the rest of the universe in that slow drift toward entropy. Cold is the direction the universe is heading. This star has simply arrived early. If you could stand inside the nebula, if you could somehow remain safe and warm amidst the chill, you would witness a landscape built from motion's absence. Light scattered into pastel blues, dust suspended in a silence that feels ancient, a dying star hidden behind its final breath. It would feel like visiting the end of time, like seeing the universe's future wrapped inside a frozen moment. For now, it is the coldest natural place we have ever found, a threshold near the limits of physics, a quiet example of how nature does not always need violence to create extremes. Sometimes, all it takes is letting go. The Boomerang Nebula is a star's final exhale, turned into the deepest chill the cosmos can allow. And as we look into this frozen wonder, another question emerges. If dying stars can fall below the universe's temperature, what other secrets does extreme cold reveal? What else happens when motion slows almost to zero? We drift onward, toward the physics of expansion, the beauty of freezing light, and the strange truth that silence can be colder than the universe itself. Part 4. Breathing out a star, cooling through expansion. Just like air from your lungs feels colder when you breathe out, gas rushing away from a collapsing star steals heat with it. A simple thermodynamic truth scales up to cosmic size and turns a nebula into a freezer beyond comprehension. This gentle law of physics, that expanding gas cools, is one of the quiet architects of the universe. It shapes atmospheres, it controls weather, and in the distant reaches of space, it becomes powerful enough to rewrite the thermal limits of nature itself. Here, cooling isn't caused by winter winds or ice-covered landscapes. It is written into the motion of gas as it stretches outward into the vastness of vacuum. To understand this cosmic chill, imagine standing beneath a star at the end of its life. Inside its core, nuclear reactions that once burned fiercely now soften. Fusion slows, pressure weakens. The star begins to collapse under its own gravity, a slow inward sigh that triggers a dramatic outward response. Layers of hot material are pushed away into space, a final breath carrying its stolen warmth. As this gas expands, it spreads thin. Its particles collide less often. Energy, once dense and vibrant, becomes diluted. Heat is lost not to surrounding matter but to emptiness itself. This is the essence of adiabatic cooling, a word both complex and quiet. A word that means expansion is enough to bring about cold. Even here on Earth, you feel this truth every day. Compressed air sprayed from a can chills your skin. A breeze cools as it leaves your lungs. A cloud forms when rising warm air expands and cools high in the sky. The universe simply takes the same rule and applies it with more space and far more silence. Now return to the boomerang. Nebula for a moment, the coldest natural place known. That extraordinary chill comes from gas being forced outward from a dying star faster than heat can chase after it. No flames linger. No radiation remains strong enough to hold motion in place. The result is a temperature almost unthinkably low, just 1 Kelvin above absolute zero. That cold exists because expansion there is not gentle. It is explosive. The star's outer atmosphere streams away with incredible speed, carrying thermal energy into the dark where it cannot remain gathered. The gas is stripped of warmth so completely that it falls below even the background warmth of the universe. This is cooling through expansion perfected. Inside every expanding nebula, this same quiet physics unfolds. Stars nearing their end lose the battle against gravity. Their atmospheres drift outward, and the heat that once built planets and lit skies becomes spread across impossible distances. A star breathes out, and the night grows colder. In many such nebulae, we can see wind-blown sculptures of matter, ribbons and shells and arches shaped by the star's changing pulse. Each layer a memory of what once burned within, each layer colder than the last. As gas expands into space, a new dynamic begins. Radiation from the star thins and flickers. Temperatures plunge, atoms slow. Molecules that could not survive in heat now form fragile bonds in the cold. Carbon binds with oxygen, forming carbon monoxide. Hydrogen molecules drift like spectral fog. In the Boomerang Nebula, even complex molecules appear because conditions are gentle enough for chemistry to proceed slowly, precisely. Here, cold becomes a cradle for delicate structure. On cosmic timescales, this expansion-driven cooling does more than freeze gas. It prepares the universe for its next chapter. Stars don't simply vanish when they die. Their remains are recycled. What cools today may ignite new worlds tomorrow. When enough cold matter gathers again, gravity will call it back inward. Nebula becomes star. Star becomes nebula. Warmth becomes cold, and eventually warmth again. The universe breathes, a slow cycle of fire and frost. And yet, even as cold spreads outward from dying stars, the stars themselves have their own strange reactions to expansion. Some stars swell into red giants, their outer layers drifting so far from the core that they cool dramatically. Their surfaces become dim, almost gentle, even as their hearts burn with last reserves of fury. Expansion doesn't just cool clouds, it cools suns. Heat becomes a rare treasure, locked away at a star's shrinking center. Eventually, gravity wins the struggle entirely. The core collapses to become a white dwarf. small, dense, brilliant with leftover heat, while the surrounding gas continues drifting into the dark, growing colder with every kilometer it travels. The scale of this cooling is nearly impossible to grasp. A single breath from a dying star can expand over distances thousands of times greater than the size of our entire solar system. A single gasp can chill matter for millions of years. We do not measure this cold in seasons, we measure it in epochs. In the end, as the nebula fades into invisibility, only the memory of that expansion remains in the temperature of the dust that lingers. That dust may one day become part of another star, another furnace rising out of cold. But for a while, a long while, it will stay frozen near the lower limits of physics. Expansion is the universe's great exhale. Contraction is the inhale. Everything in the cosmos joins this rhythm. Gas clouds expand into the void. Then, later, they fall inward under gravity, forming new suns ready to burn again. It's a cycle written across galaxies, cooling through expansion, heating through collapse. Motion defines temperature, change defines time. The universe does not cool all at once. It cools wherever energy stops gathering. And the emptiness of space is the perfect place for warmth to disappear. Tonight, as you rest, every molecule of air around you hums with heat from the sun. But if that air drifted upward and outward into the vacuum above the atmosphere, it would cool into stillness, just like the gas escaping a dying star. What feels like a breath to you feels like eternity to the cosmos. This is the quiet truth that expansion teaches, that cold is not punishment, but the natural result of letting go. A star exhales, a nebula forms. And in that exhale, the universe reveals its deepest calm. As we continue this cold journey into the cosmos, another question rises gently. What happens when expansion slows so much that motion nearly disappears? What hidden structures emerge from atoms moving only in whispers? In the next part, we drift into a place where chemistry changes under such deep cold, a realm where molecules behave differently and the building blocks of life freeze into patience. Part 5. Why Absolute Zero Can never be reached. There exists a lower boundary to temperature, absolute zero, where motion stops entirely. But the laws of quantum physics refuse to allow stillness. Even in perfect cold, particles must hum with a faint whisper of energy. Absolute zero, 0 Kelvin, 273,415 is the temperature at which thermal motion should completely vanish. No vibrations, no collisions, no sound or agitation in the fabric of matter. It represents the idea of perfect silence within atoms themselves. A frozen moment in which energy has nowhere left to go. It sounds simple, even familiar. Cold things slow down, cool them more, and they slow further. Eventually, something must reach the bottom. Yet the universe does not allow that final step. It keeps a tiny ember of motion alive deep inside every particle. Because stillness is impossible under the rules that govern the very small. To understand why, we have to explore a microscopic truth that lies beneath the world we feel, a truth so strange that physicists spent decades learning how to even describe it. In the everyday world, cold is just a measure of how much things move. A cup of water cools as its molecules drift slower. Metal shrinks slightly as its atoms become less restless. A winter night stiffens the world because energy escapes into the air. Heat is motion. Cold is the loss of motion, so if we can slow motion enough by removing heat, why can't we reach zero? Why is the universe protecting that last whisper of energy? The answer lives inside quantum mechanics, the behavior of electrons, atoms, and subatomic particles that never obey the tidy rules of classical physics. On the smallest scales, motion is not optional. Particles flicker with what's called zero-point energy, the baseline hum of existence. This energy cannot be removed because without it, the particle would have a precise location and precise stillness at the same time, something the universe forbids. Here we meet one of the quiet, pillars of physics, Heisenberg's uncertainty principle. It tells us that the more precisely we know where a particle is, the less precisely we can know how it's moving. and vice versa. If we forced a particle into complete stillness at absolute zero, we would know both: its exact position and that its velocity is zero. Nature refuses that certainty. Particles must move, even if only the tiniest amount. The quantum world insists on uncertainty as a kind of built-in motion. Motion protects reality from perfection. Absolute zero is also impossible because temperature depends on exchanging heat, letting energy flow from one thing to another. But as you approach that lower limit, the universe becomes reluctant to give up those last scraps of motion. Like trying to remove the final drop of water from a sponge, physics gives more resistance the closer you get to empty. Every attempt to cool something further requires exponentially more effort. You can get astonishingly close. Researcher-built cryogenic systems have chilled atoms to billionths of a Kelvin above absolute zero, but never zero itself. Even in the vacuum of space, even in the universe's coldest nebulae, background radiation keeps everything slightly awake. Cold can grow deep, but not perfect. This rule isn't just philosophical. It holds the cosmos together. Without zero-point energy, electrons would collapse into atomic nuclei. Atoms would lose their size and structure. Chemistry would cease. Matter itself would vanish into stillness. The faintest motion is the scaffolding of existence. It keeps atoms balanced in place, orbiting pockets of probability. It gives the universe texture, a quiet vibration beneath everything we see or feel. Absolute zero would unmake reality. So reality forbids it. Even time would behave differently if motion ever stopped. Temperature is a measure of how systems change. Without change, time loses meaning. There is no before or after if nothing moves, vibrates, or transitions. In a perfectly frozen universe, all events would halt. The story of existence would become a single frame with no next page. Time, like heat, is bound to motion. As long as energy continues to move, even imperceptibly, the arrow of time survives. This is the strange comfort of zero-point energy. It keeps time alive. But if absolute zero can never be reached, can it at least be imagined? Physicists model it as a limit, a boundary we can approach but never cross, like a horizon that retreats as you chase it. In laboratories, scientists have used magnetic traps and laser cooling to bring atoms close to that edge. They manipulate tiny clouds of matter until motion slows to near silence. These experiments create something extraordinary. Bose-Einstein condensates, matter cooled so far that atoms share a single quantum state. Separate identities blur. A crowd of particles behaves like one. Here, the quantum world grows large enough to touch. Atoms become waves. Waves become a single shape. Particles act with a quiet unity in place of chaos. This is the closest our universe has ever come to absolute stillness. But even here, motion lingers. Even here, zero remains unreachable. Nature's laws do not treat limits as goals. They treat them as fences. The speed of light, an upper boundary that cannot be exceeded. Absolute zero, a lower boundary temperature cannot cross. The universe runs between these walls like a river inside canyon stone, guided, shaped, protected from extremes it cannot sustain. Stillness is one such forbidden extreme. The quantum heartbeat is always faint but always present. Absolute zero becomes not a destination, but a reminder. Motion is fundamental. Even space itself resists total calm. The vacuum, what we imagine as nothingness, is not empty. It seethes with fluctuations. Particles and antiparticles pop briefly into existence, then vanish. Energy is borrowed and returned in an endless, invisible dance. This is the quantum vacuum, where creation and destruction flicker constantly beneath awareness. If the vacuum cannot be perfectly still, nothing within it can stop moving either. Stillness is not the universe's nature. Motion is. So when we talk about the coldest places in the cosmos, regions where motion barely exists, where molecules hesitate to interact, we are still talking about motion, just less of it. The Boomerang Nebula, with its 1 Kelvin chill, is astonishing not because it's absolutely cold, but because it is nearly as cold as physics allows. Nearly, but never perfectly. The universe keeps a quiet pulse alive, a hidden heartbeat that echoes through every particle, every atom, every star and nebula. Absolute zero is the bottom of the cosmic thermometer, visible but unreachable. It is the line the universe draws between existence and the absence of existence. So as we drift forward in this quiet journey, remember that even in deepest cold, nature never stops completely. There's always a hum beneath the silence, a tiny vibration that keeps the universe breathing. And as motion slows to its limit, another question waits just ahead. If stillness is impossible, how does the universe continue to cool? What happens as stars fade and the cosmic temperature keeps falling toward a boundary it cannot cross? In the next part of our journey, we step into the spaces where darkness becomes powerful, where the absence of light steals heat away faster than stars can give it, revealing the strange influence of shadows in the coldest corners of the cosmos. Part 6. When darkness becomes a force. Light warms everything it touches. Where there is no light, there is no rescue from the cold. The universe's greatest refrigeration system is emptiness itself, a void that steals heat faster than stars can give it away. Darkness is more than the absence of light. It is a physical environment, one that shapes the fate of heat itself. Here on Earth, night is temporary. The sun always returns. But in the vastness between stars, night is the permanent state. Cold is not something that arrives. It is something that remains when nothing pushes back against it. To understand this, imagine standing in space with no nearby sun. Your body radiates heat outward every second, losing energy to a darkness that never returns it. There is no air to insulate you, no ground to reflect warmth. Energy leaves, and nothing replaces it. Darkness takes, quietly and efficiently. Every warm object in the universe continuously glows, not always in visible light, sometimes in infrared, in microwaves, in faint whispers of radiation. This glowing is heat leaving. It is the natural direction of energy, from warm places outward. In empty space, there is no limit to that escape, no molecules to hold warmth in place, no protective hand to cup heat near its source. Stars themselves burn not because the universe gives them heat, but because they produce their own fast enough to delay the inevitable cold around them. Turn off a star, even for a moment, and the cold would win. Light is the only barrier. Darkness, the inevitable truth. We think of cold as something that spreads, but in space, cold doesn't move. It simply exists. It is the baseline. Heat must constantly fight to carve out small pockets of warmth against a universe eager to erase them. A hot object in darkness loses energy like water pouring through open fingers. This loss is called radiative cooling. Every star, every planet, every spacecraft is an object constantly cooling into the void. Even our sun, a furnace of nuclear fury, loses heat into darkness faster than any other place except inside its own core. Without constant nuclear fusion, its energy would drain into the void until the star's light faded into a final sigh. All warmth is temporary. Darkness is patient enough to wait. Some places in the universe experience darkness so deep and so thorough that the cold becomes nearly perfect. Deep space shadow is different from any shadow on Earth. Here, a shadow is merely an absence of sunlight, temporary nightfall. But imagine a crater at the moon's south pole, a place the sun has not touched for billions of years. Temperatures there plunge near absolute zero. Why? Because without light, the surface cannot stop the endless drain of thermal energy into space. Nothing replenishes the warmth. Nothing interrupts the cooling. Darkness becomes a force. Planets with thick atmospheres have a shield against this draining chill. Earth's greenhouse gases trap warmth, preventing energy from radiating directly into space. Our nights may cool, but never like the exposed skin of bare rock in the cosmic wind. Strip a planet of its protective blanket, and darkness consumes its warmth quickly. Mars, for example, loses heat so rapidly each night that temperatures swing wildly. Its thin atmosphere cannot defend against the vacuum waiting just above the sky. A world without insulation? is a world surrendered to shadow. This cosmic drain is so powerful that even starlight cannot prevent the universe's cooling. Every second, countless photons stream outward into the darkness, traveling forever unless they strike another object. Most never will. Their journey continues into infinite night, spreading thin, energy diluted to almost nothing. This is one reason the universe cools over time. Heat disperses into a vast volume that grows larger each moment. Darkness expands, heat dissolves into it, yet darkness is not hostile, it simply is. The default state of everything. Warmth requires structure, fusion reactions, collisions, chemical exchanges, all built upon the fragile balance of motion and energy. Cold requires none. Even a star, a bright miracle of physics, is surrounded by darkness far stronger than its light. Its warmth reaches only a tiny sphere compared to the emptiness beyond. If the Milky Way were viewed from afar, our sun would appear not as a spotlight, but as a single candle lost in a cathedral. In the early universe, light had nowhere to run. Everything was dense. Photons collided constantly with matter, trapped in a glowing fog. As expansion began, that fog cleared. Light found new paths and darkness found its power. The cosmic microwave background, the cooling echo of the Big Bang, is evidence of this transition. Light stretched into weakness, warmth surrendered to the void. The future continues that direction. Stars burn out, galaxies drift apart, black holes evaporate, even radiation loses energy as space itself expands. Darkness wins, not through violence, but through patience. You might think cold is the enemy of motion, but some of the universe's most mysterious phenomena depend on extreme chill. In the silence of deep cold, electrons can flow without resistance. Matter becomes quantum in scale, as if atoms remember they are waves. In that flicker, between motion and stillness, strange states emerge. Superfluids, superconductors, Bose-Einstein condensates. Cold reveals hidden beauty. Darkness brings new possibilities. The universe does not fear the freeze. It grows in its silence. When we look up at the night sky, we see stars as points of light. But what fills most of the sky is the blackness surrounding them. That blackness shapes everything. It defines the rarity of warmth and the fragility of light. It holds the entire cosmic balance between motion and stillness. Darkness is not empty. It is the environment in which all structure is built. It quietly removes energy until only the essential remains. So as you drift tonight into your own darkness, a bedroom dimly lit, eyes slowly closing, remember that the quiet around you is not a threat. It is the most common condition in the universe, a calm backdrop against which every spark of motion becomes meaningful. The coldest places in space are not frozen because something chills them, but because nothing warms them. Darkness is the steady pull downward, gravity's partner in the thermal fate of the cosmos, and as warmth fades across time, darkness will continue to rise not as an enemy, but as the universe's natural rest. As we continue deeper into this frozen journey, another question unfolds softly before us. If darkness can steal heat away, what shapes remain when motion slows almost to nothing? In the next part, we explore the delicate chemistry of deep space, a realm where molecules wait in ancient patience for the spark of warmth that might someday awaken them. Part 7. Stars that freeze themselves. Dying stars often cool as their atmospheres expand. The same power that once forged elements and ignited fusion begins to stretch thin, until the furnace collapses into silence. A star's life is a balance between two forces, the outward push of heat and the inward pull of gravity. As long as a star has fuel, hydrogen, to fuse into helium, heat pushes outward fiercely enough to hold gravity at bay. The star shines, stable and strong, a beacon against darkness, but nothing burns forever. When fusion slows, the balance shifts. Gravity begins to win. At first, the star fights back. In desperation, its core contracts heating further. Heat surges outward, inflating the star's outer layers dramatically. A red giant rises, swollen, luminous, yet cooling on its surface. The star has grown larger, but its heat, now spread thin, reaches the edge of the atmosphere like the final breath of a fire. This is the beginning of cosmic winter. Think of the star as a campfire in the cold. When the wood burns bright, warmth spreads easily. But when the flames fade, the heat stretches out too far and the fire loses its focus. What once warmed everything close now flickers into chilly distance. Stars suffer this same fate. As they expand into giants, their vast surfaces cool dramatically, from thousands of degrees to mere fractions of their youthful brightness. They glow red, not with the fierce white heat of youth, but the gentle embers of age. Yet the core becomes a paradox, smaller, hotter, more frantic. Gravity crushes it tighter, forcing it to ignite new fuel if it can. Helium into carbon, carbon into oxygen, each step buying a little more time, a little more warmth. But eventually, the fuel runs out completely. The fire goes out. Without outward heat, gravity collapses the core swiftly. The once mighty star shrinks from a giant to something the size of a planet, a white dwarf, a hot ember of what was once a sun. This ember shines only because of leftover heat. Its glow is memory, stored warmth slowly radiating into darkness, and over billions of years that remnant cools. Its light fades, its heat escapes into the void, surrendering to the universe's quiet pull toward stillness. In the far future, so far we can barely comprehend, white dwarfs will cool into black dwarfs, invisible spheres of crystallized matter, colder than the deepest night. These stars freeze themselves into silence. There are other endings, more dramatic and more chilling. Stars far larger than our sun burn fuel so violently that their deaths are explosive. A core collapse triggers a supernova, a flash brighter than a billion suns, casting material into space at impossible speeds. But after the explosion, a new kind of cold emerges. Sometimes the core becomes a neutron star, a city-sized object of pure compressed atoms. In their first moments, neutron stars are unimaginably hot, but they cool faster than any object known, their heat radiating into the void until they become silent, dark spheres of nuclear matter. Still more massive stars collapse further still, into black holes, where heat, light, and time are swallowed whole. No glow, no warmth, only gravity and the cold horizon of the event boundary marking where heat can never escape. But not all. Cosmic cooling comes in a sudden collapse. Some stars sculpt their own freeze-out slowly, casting off atmosphere in beautiful expanding shells. Planetary nebulae, like delicate cosmic butterflies, form from stars like our own shedding their outer layers gently. The gas drifts outward and cools. Dust grains form. Molecules assemble in the cold. The star remains at the center, small and fierce, but increasingly distant from the warmth it once shared. That distance grows with time until the outer shells become frozen record books, pages of material written by light, now waiting in stillness. Even in death, stars leave behind chemistry that may one day be warmed into planets, oceans, and life. Cold is the pause between chapters. And then there is the most ironic freeze of all, the cooling brought on by excessive heat. Near the end of fusion, some stars burn so violently that they blow off matter faster than heat can travel through it. The star creates its own deep chill through pure expansion, cryogenic self-destruction. It is the mechanism behind the Boomerang Nebula's record-breaking cold. The star breathes out too fast for warmth to follow. Its outer layers stretch thin and lose motion. Temperature falls below the cosmic background. The universe's coldest places exist not through lack of heat, but through abundance released too quickly to hold. On Earth, we equate cold with fragility. Ice breaks, water freezes, life struggles. But in space, cold can be a kind of preservation. Frozen nebulae hold the raw ingredients of planets. Dust and gas wait in suspended animation for gravity's return. In the silence of cold, atoms can settle into stable bonds that heat would destroy. Organic molecules, the earliest hints of life, form in dark, frigid clouds between the stars. What looks like an ending is really preparation. Stars freeze themselves so something new can one day ignite. Our sun will follow this path. 5 billion years from now, it will swell into a red giant, its heat stretched thin across the widening sky. Earth's oceans will boil, then vanish into space. The sun's heart will shrink into a white dwarf ember glowing faintly against the black, and slowly, patiently, it will cool, joining the countless other stars that have slipped into cosmic hibernation. The universe keeps time not by heartbeats, but by the cooling of its fires. A star's death is colder than anything we can imagine. Not because cold rushes in, but because heat escapes without replacement. Every warm thing in existence is losing heat right now. Every star, every world, every atom. The universe trends toward coldness as surely as stones fall to the ground. Entropy is the slow cooling of possibility, a gentle drift toward stillness that nothing can halt completely. Stars freeze because everything does, but this coldness is not sorrow. It is the balance of cosmic motion. It is a promise that when light returns, it will return meaningfully. In the vast calm of low temperatures, a kind of order arises, crystals forming inside dead stars, molecules assembling in dark clouds, galaxies sculpted by the gentle hands of thermodynamics in time. Cold is the universe resting, preparing, waiting. As our journey continues, our next question emerges softly. If the cold preserves matter and darkness steals heat, what forms arise in that stillness? What hidden architectures build themselves in the quiet, deepest cold? In the next part, we explore the chemistry of near absolute zero, a realm where patience becomes creation and the universe shapes its most delicate structures in silence. Part 8. The cold chemistry of deep space. In regions so cold that molecules barely move, strange chemistry occurs. Atoms cling together not through heat and chaos, but through the quiet patience of near absolute zero. When we think of chemistry, we imagine heat and reaction, flames, boiling liquids, energetic collisions. But the universe tells a calmer story. In the silent cold between the stars, molecules form not through violence, but through stillness. There, in temperatures just a few degrees above absolute zero, atoms drift like slow dancers, meeting gently, bonding delicately, assembling structures that heat would instantly destroy. Deep space is the universe's most patient laboratory. It does not rush change. It lets chemistry happen on the timescale of eternity. Consider the great molecular clouds that drift between stars. They are dark and frigid, sometimes just 10 Kelvin above absolute zero. There's almost no light, no stirring breeze, no crowded collisions, just quiet. At these temperatures, atoms barely move. Their energy is so low that when they meet, they tend to stay together. Hydrogen, the most common element in the cosmos, begins to pair into H2 molecules, forming the foundation of interstellar chemistry. On the surfaces of tiny dust grains, other elements join the dance. Oxygen, carbon, nitrogen, all assembling into simple molecules like water, carbon monoxide, ammonia. These frozen particles become seeds, invisible specks that carry the ingredients of life from one star system to the next. Heat breaks, cold builds. In these shadows, something remarkable occurs. Organic molecules, complex chains of carbon and hydrogen, take shape without life to guide them. Astronomers using radio telescopes have detected alcohols, sugars, even amino acids floating in the calm void between stars. A single molecule forming in these conditions may take thousands of years. But time is plentiful here. The universe does not hurry creation. Within clouds like the Taurus Molecular Complex and the Orion Nebula, this chemistry unfolds on scales so vast that entire solar systems inherit their frozen chemistry at birth. Stars may ignite violently, but the ingredients that build their planets are gathered in deep quiet first. Life is born from cold patience long before warmth awakens it. These environments are so cold that quantum behavior becomes noticeable even at scales larger than the atom. Electrons can shift from one molecule to another without crossing the space between, a phenomenon called quantum tunneling. This is chemistry without collisions, reaction without impact, movement without motion. At warm temperatures, reactions rely on force and speed. In deep space, they rely on probability and subtlety. The universe becomes an artist of precision in the absence of heat. The clouds where these transformations happen are also the birthplaces of stars. Gravity slowly gathers dust and gas, pulling material into dense regions that collapse inward. And during this collapse, the cold chemistry sealed in those grains of dust is carried into the forming planetary disks. Water ice, built in the darkness, rides inward to worlds where light will eventually shine. Organic molecules, barely formed, become the alphabet that life may someday use. Every ocean may begin as a frozen molecule in a silent cloud. Every cell may trace its origins to chemistry that required unimaginable stillness. Cold does not hinder creation here, it preserves it. Even comets, travelers from the cold outskirts of solar systems, carry this ancient chemistry. When they pass near a star and heat up, they release the frozen molecules they have carried for billions of years. Many scientists believe that Earth's first water and organic compounds may have arrived from such icy messengers. We drink the chemistry of deep space. We are built from its dust. The most frigid regions of the universe hold the most delicate beginnings of life. Yet the calm of deep space does not last forever. Once a star ignites, its radiation begins to tear molecules apart. Ultraviolet light breaks chemical bonds. Heat scatters the fragile constructions. But even in the face of violent starlight, cold chemistry persists, just beyond the reach of illumination. The shadows of protoplanetary disks, protected from a star's fierce glow, frozen chemistry continues its slow development. Astronomers peering through ALMA and JWST have discovered icy rings around young stars rich in carbon chains and simple sugars, the ingredients of complexity waiting for warmth to stir them awake, like seeds awaiting spring. Perhaps the most surprising role of cosmic cold is the creation of dust grains, tiny crystals of silicate, carbon, and metal. Below certain temperatures, atoms settle into long, orderly structures, like snowflakes forming in the sky. These grains act as scaffolding on which molecules gather. Dust is the universe's shelf space. Without it, chemistry would drift apart before it ever became meaningful. And so the cold builds not just molecules, but architecture. The groundwork for planets is laid in silence. Everywhere we find cold in the cosmos, we find the possibility of life. Not life itself, but its most essential preparation. Consider the dark clouds that float at the galaxy's edge, barely touched by starlight, colder than anything we can imagine on Earth. They appear empty, but inside, they are busy with slow creation. Every infrequent collision adds to a growing library of chemical potential. From cold comes abundance. From stillness comes structure. The universe's deepest freeze becomes a place where life's spark gathers its fuel. As we look farther out into space and deeper into the past, we discover something beautiful. Cold came first. Before stars, before planets, before warmth and fire, there was chemistry, silent, patient, waiting for the moment heat would arrive to tell the molecules, move. Then, light would meet structure, energy would meet possibility, and life would find its path. Warmth may awaken life, but cold builds the stage. Tonight, as you close your eyes, every breath you take contains atoms older than stars. They formed from ancient chemistry in the universe's earliest cold. They traveled through silence to become part of you. You are built from the patience of deep space. And as we continue our journey into the coldest truths of the cosmos, another question emerges like frost. If the earliest chemistry forms in such deep cold, what other wonders take shape when matter freezes even further? In the next part, we will travel into the hearts of dying stars, where matter cools into crystal and the universe forms diamonds the size of worlds. Part 9. How we measure the cold of the cosmos. No thermometer could survive the void, so astronomers use light, the glow of dust grains, the sway of molecules, the silent signatures that temperature leaves behind in radiation. To measure the cold of space, we must observe something that doesn't want to be seen. There is no air. There is no wind. Objects in the void do not share warmth with neighbors because they have none. Heat doesn't fade by touch, it escapes by light. When a star, a dust cloud, or even a Lonely rock cools. It releases energy into the dark as faint electromagnetic whispers. And those whispers are what astronomers listen for. Everything with a temperature above absolute zero emits radiation. The colder the object, the longer its wavelength. Warm things glow with visible light. Cool objects glow in infrared. The coldest regions glow in microwaves. Temperature is not a number in space. It is a shape of light. Imagine a snowball melting in sunlight. It glistens because it reflects the star above. Space works differently. Light travels in straight lines and rarely reflects. So scientists measure an object's own glow, even if that glow is unimaginably faint, to learn how warm or cold it is. Telescopes tuned to different wavelengths let astronomers read temperatures across the universe. Infrared telescopes detect cold dust at a few hundred Kelvin. Sub-millimeter instruments find clouds below 30 Kelvin. Microwave detectors trace the cosmic background near 3 Kelvin. Even a region colder than the universe itself reveals its chill by how little light escapes from it. The darker the glow, the deeper the cold. One of the most powerful tools is a concept called blackbody radiation. A perfect blackbody absorbs all light that hits it and emits a spectrum of light that depends only on temperature. As something cools, its emission shifts from visible light to infrared to microwave, and eventually toward wavelengths so long that detecting them requires extraordinary sensitivity. Astronomers can examine that spectrum and see a thermal fingerprint, a smooth curve that reveals temperature without ever needing to touch the object. The universe leaves its diary written in wavelengths. Molecules themselves give away temperature. When atoms bond, they vibrate and rotate. These motions depend on energy. Faster motion, warmer temperatures; slower motion, colder temperatures. By measuring the rotational and vibrational lines within a molecule's spectrum, scientists can watch motion slow almost to silence. A star-forming cloud, billions of kilometers wide, can tell us its temperature by how gently molecules sway within it. In some of the coldest molecular clouds, astronomers find rotation slow enough that the difference between one energy state and the next can take thousands of years to change. Time stretches when motion fades. Even dust grains, microscopic, ancient, carry temperature in their glow. Cosmic dust absorbs starlight and then releases that energy as faint infrared radiation. By comparing how much light dust absorbs to how much it re-emits, astronomers can track how cold it is. In regions far from stars, dust becomes so cold that only the universe's faint background radiation keeps it above absolute zero. Wherever dust exists, a thermometer exists. And then there are cosmic shadows, places where light refuses to go. Inside deep craters on the moon, permanently dark and shielded from the sun, temperatures plunge below 40 Kelvin. The cold is measured by the lack of thermal emission in NASA's infrared detectors. Darkness allows heat to escape until just a whisper of radiation remains. The shadow becomes a measurement tool. The absence becomes a number. Even entire galaxies can be weighed in temperature, not by their stars, but by their cold gas. Astronomers measure the 21-centimeter hydrogen line, a specific radio wavelength emitted when a hydrogen atom's electron flips its spin. How strong that line appears reveals how warm or cold interstellar hydrogen has become. Across the Milky Way, vast pools of hydrogen gas sit at 100 Kelvin or below, waiting for the gravity of some future star to call them inward. Cold maps the future of light. The coldest known natural region, the Boomerang Nebula, did not reveal itself by chance. Its astonishing temperature was discovered because it emits less radiation than the cosmic microwave background. The universe glows at a stable 2.7 Kelvin. If something glows even less, it must be colder. Astronomers pointed telescopes into that thin patch of nebula and found a thermal silence deeper than anywhere else recorded. Cold announced itself through the quiet. The tools that unlock these secrets grow more precise each decade. The James Webb Space Telescope reaches into the mid-infrared to detect gentle warmth from dust around newborn stars. The Planck satellite mapped the entire sky in microwaves, revealing the universe's thermal history in exquisite detail. Ground telescopes like ALMA in Chile's Atacama Desert observe the chemistry forming inside cold molecular clouds with resolution humanity once only dreamed of. Every new observatory rides deeper into the cold. We are building telescopes to measure silence. There's a quiet paradox in this effort. The colder an object is, the harder it is to detect. And yet some of the most important truths are locked inside that cold. Life, in all its complexity, requires molecules that cold space assembles. Stars, before they shine, are carved from frozen matter. Even the universe itself began hot and has since spent billions of years learning how to cool. To understand temperature in space is to understand the arc of time. As we listen to the universe this way, one message becomes clear. Warmth is local. Cold is universal. A star may blaze, but darkness surrounds it with infinite patience. A planet may host life, but the cosmos waits to reclaim its warmth. Temperature shows us where energy gathers and where energy fades. It shows us what lives and what rests. It shows us not just the present, but the direction of the future. Tonight, if you look at the night sky, you will see only the bright things, stars, planets, galaxies. But the true shape of the universe is drawn in the dark spaces between them. That is where the deep cold lives. That is where new worlds begin. That is where heat eventually returns. The cold of space is not absence, it is destiny. As we drift forward into the next part of this journey, a deeper question rises. If the universe keeps cooling, and if we can read that cooling in light and motion, what happens when even stars stop burning? What does matter become when heat fades to its last whisper? In the next chapter, we travel to the hearts of dying stars, where matter freezes into crystal and the universe builds diamonds the size of continents in the deep calm of time. Part 10. Time slows in the cold. Where atoms move slower, change itself becomes hesitant. Cold stretches seconds longer, a soft resistance against the universe's usual rush toward disorder. Time and temperature are woven together. When motion is lively, seconds pass filled with activity. Atoms colliding, molecules reacting, matter changing. But in the deepest cold, motion slackens. Reactions stall, decay waits. The universe inhales and holds its breath. It is not that clocks physically change their speed, but the processes that clocks measure, the unfolding of physical events, progress more slowly. In cold, the future does not hurry. At a comfortable room temperature on Earth, particles vibrate constantly. Electrons leap between energy levels. Chemical reactions snap and spark. Life is busy with motion. Now imagine plunging those same atoms into a frozen region of space where the temperature barely rises above absolute zero. Their dance becomes a near statue. Electrons hesitate, vibrations soften until they are mere whispers. The pace of transformation slows to a crawl. This delay is deep. Chemical changes that take moments on Earth may require centuries in the void. Cold isn't just a temperature, it's a kind of stillness in time. Even biological time feels different in cold. Food preserves longer in freezers because life's chemistry pauses. Bacteria stop dividing. Spoilage freezes mid-step. Nature uses cold as a memory tool. Frozen seeds retain their potential long after. The warmth that created them has faded. Deep within glaciers, ancient creatures, even viruses, sleep in perfect pause. Time has moved forward outside, but for them, not a second has passed. Cold protects possibility by slowing the march of entropy. Space is the ultimate freezer. In shadowed craters on lonely moons, in drifting clouds between the stars, material waits. Dust grains gather molecules, but keep them locked in place for thousands, even millions of years until heat lets them move again. A world can form slowly because cold keeps its building blocks from reacting prematurely. Creation requires patience. Cold grants that patience. The relationship between cold and time lies at the heart of thermodynamics, the science of heat and change. Entropy, the measure of disorder, tends naturally to increase, but when temperature drops, entropy's advance slows, systems resist change, order holds longer. Cold is like a gentle brake on the universe's expansion into chaos. Even stars feel this break. White dwarfs, the remnants of suns, cool so slowly that it takes billions of years for their heat to fade. Time becomes stretched thin. A star that once lived fast now rests in slow motion. Quantum physics reveals another layer of this connection. At extremely low temperatures, particles behave less like bouncing objects and more like soft waves, merging into shared states that endure far longer than motion-filled matter would allow. In laboratories on Earth, scientists create Bose-Einstein condensates, clouds of atoms cooled to billionths of a degree above absolute zero. Inside these laboratory wonders, particles stop acting as individuals. They share one unified existence, as if time applies to them collectively instead of separately. Events slow, motion becomes precise, quantum effects bloom large enough to observe. Cold does not merely slow time, it transforms what time means. In deep space, a similar quantum stiffness may occur inside dying stars. White dwarf interiors are so cold and dense that matter crystallizes, atoms locked into cosmic diamonds the size of worlds. Crystals are orderly. They hold their structure with strength. They resist the pull toward entropy. They age at an astonishingly slow rate. A crystallizing star is time taking shape. The entire universe is cooling with age. After the fire of the Big Bang, temperature has steadily dropped for nearly 14 billion years. As the cosmos expands, energy spreads thinner, motion calms, entropy still grows, but the pace slows as there is less heat left to release. The far future the universe approaches will be incredibly cold, a winter not of seasons, but of physics. Stars will burn out, galaxies will drift apart, black holes will evaporate through Hawking radiation over unimaginable spans of time. In this distant destiny, change itself will become rare. Reactions will pause, motion will fade, time will become wide and empty, a slow dream the universe barely remembers having. Cold and time will become nearly the same thing. On human scales, we feel this subtly. In winter moments, a calm snowfall, breath hanging in the air, time feels slower, not just emotionally but physically. Atoms move less, sound travels differently, reactions in your body cool slightly. Everything pulses a little more gently. Cold quiets us because it quiets the world all the way down to electrons. This connection between cold and time has a practical power on Earth. Deep freeze labs preserve cells, genetics, embryos, slowing biological aging to nearly zero. Cryogenics aims to keep delicate systems alive until the right moment for warmth to return. Cold is not death, it is the protection of potential. The universe follows this rule too. Frozen comets carry chemistry across millennia. Icy moons store oceans beneath crusts of stillness. Dormant molecules wait for a chance to awaken. Cold holds the future safe until time is ready. Even in your own experience, time's relationship to temperature whispers in mundane ways. A hot drink cools quickly. A cold drink stays cold longer. Heat races outward. Cold resists change. Events unfold differently based on how much motion they contain. The universe simply applies this rule on a scale so large we rarely notice its power. So as we journey through the coldest places in the cosmos, we discover something profound. Cold is not emptiness. Cold is patience. It shapes the pace at which stars evolve, planets form, and life emerges. It stretches seconds into centuries, moments into eras. Time does not stop in the cold. It simply takes its time. As you lie in stillness now, with your breath slowing, your heartbeat calming, you can feel a tiny echo of the universe's deepest chill. Your body cools and your mind drifts into a different rhythm, one unhurried by daylight or urgency. Sleep, too, is a kind of cold, a soft slowdown, a pause where time releases its grip. And as we continue this journey deeper into the frozen truths of space, another question forms quietly. If time slows in the cold, what happens when matter freezes into perfect stillness? What secrets lie inside stars turning to diamond or inside dead suns that have gone solid? In the next part, we step into that crystalline future where matter becomes eternal and cold does not destroy, but preserves the universe in silence. Part 11. frozen stars and quantum crystals. Inside ancient stellar remnants called white dwarfs, matter compresses into a crystal lattice, a star turning slowly into a diamond as it cools through cosmic time. This transformation is not like ice forming on a winter pond. It is not gentle frost layering over metal. It is matter reshaping itself at the deepest level, atoms falling into perfect order because motion and heat no longer disrupt their structure. A white dwarf is what remains when a sun-like star has spent all of its nuclear fuel. The outer layers drift away, forming a nebula, a delicate cloud glowing softly with the star's last light, while the core collapses into an object no larger than Earth, yet heavier than the sun. Inside this dense, fading ember, gravity crushes matter so tightly that electrons are forced to merge into place, their chaotic motion frozen into a rigid frame. Carbon and oxygen atoms packed together in the most orderly way nature allows. A crystal, a star becomes a jewel. The idea sounds poetic, but it emerged from physics. In 1968, astronomer Hugh Van Horn proposed that white dwarfs should crystallize as they cool. It made sense. Removing heat reduces motion, and at high enough densities, order becomes favorable. But proving it required the kind of telescope that dances in infrared, sensitive enough to see warmth fading from stars billions of years old. In 2019, using data from the Gaia Observatory, astronomers finally captured evidence. A huge population of white dwarfs showed a strange pause in cooling, as if they were holding heat inside for far longer than expected. This was the missing signal, the delay caused by a cosmic phase transition as liquid-like atoms inside the star locked into a crystalline solid. A star in the midst of becoming a diamond glows just a little longer. White dwarfs are cold by stellar standards, tens of thousands of degrees instead of millions. But cooling them further is a slow battle against the universe's thick veil of darkness. For billions of years, they radiate away heat bit by bit. Eventually, the atoms settle, they become rigid. They arrange themselves into a single, vast crystal, a structure with a beauty far beyond anything a jeweler could hope to cut. The largest diamonds in the cosmos are the remains of suns. Some are estimated to be millions of times larger than Earth's biggest gemstones. Completely pure, completely silent, it is the ultimate cold transformation. But even before crystallization sets in, white dwarfs are different from anything we know. Their matter is a degenerate quantum gas, held up not by heat or motion, but by the strange rules of the quantum world. Electrons refuse to share energy states. They build a pressure that has nothing to do with temperature, simply the pressure of being forced too close. A white dwarf does not collapse because quantum mechanics won't let its electrons sit still. This unusual support means the star can cool endlessly without losing its structure. Cold deepens without collapse. As the crystal core forms, each atom finds a place in a vast lattice. Carbon and oxygen sit locked in symmetrical precision, a cosmic cathedral of geometry. Heat struggles to pass through crystals, so the outer layers stay warm longer while the inside freezes first. The star becomes layered, a glowing skin wrapped around a dark, silent diamond heart. Over time, the skin fades too. The white dwarf cools until its light dims beyond visibility. It becomes what astronomers call a black dwarf, a star that no longer shines. No white dwarf in the universe has had enough time to reach this stage yet. The cosmos is too young. But trillions of years ahead, it will become common. Black worlds of diamonds scattered through darkness, each a monument to the stars that once burned bright. Inside these crystallized hearts, matter behaves strangely. Atomic vibrations shift from classical to quantum. Heat is stored and released differently. Sound travels faster. Pressure rises to extremes well beyond anything seen on Earth. The crystal's structure is so impressive that scientists study white dwarfs to learn more about solid-state physics under impossible conditions. We look to frozen stars to understand matter at its limits. Perhaps the most extraordinary idea is this: the universe may be filling with crystallized stars faster than we can see. Every star, like our sun, will eventually leave behind a cooling white dwarf. Not just diamonds, but spheres of ordered matter whose silence protects stories of stellar fusion and the earliest elements ever forged. Deep inside those quiet remnants is a fossil record written in carbon and oxygen, a record heat could never preserve. Cold saves memory. As we look forward to the far future, crystals inside white dwarfs hint at the ultimate fate of time. When all stars are dead and light grows rare, these silent structures will remain, the longest-lived objects in existence. They will survive long after galaxies disperse and motion nearly ceases. Matter frozen into perfect order may be the final form the universe takes before true stillness becomes possible. The cosmic fire that once raged across every corner of space will have quieted into a vast gallery of diamonds, cooling into eternity. If you could stand on one of these surfaces, though no human ever could, you would see not a shining jewel, but a smooth, dim sphere fading into the black. No clouds, no sky, just the faint glow of leftover heat escaping into infinity. Beneath your feet, billions of trillions of atoms held in perfect alignment by a cold that does not allow chaos. Walking on such a star would be stepping on order itself. Here on Earth, we have found fragments of stars' frozen hearts as rare carbon crystals within meteorites, tiny pieces of ancient white dwarfs that cooled and shattered long before our sun was born. Every diamond we hold may carry the memory of a star's last breath. We wear the jewelry of dead suns without realizing how deep its silence truly runs. As this story continues, the universe cools. Stars burn and freeze. Matter shifts from plasma to solid. Chaos yields to precision. Cold is not the end of matter, but its most refined expression. And so, a question forms softly in the dark that surrounds us. If even stars freeze, how far can cold go? What happens when heat death approaches, when the universe becomes a graveyard of crystal suns and wandering dust? In the next part, we drift toward that distant future, a time when all warmth fades, when motion becomes myth, and the universe embraces its final chill. Part 12. The heat-death horizon. Far ahead in the universe's future lies a chilling prophecy, a time when all stars dim, all motion fades, and the cosmos enters its final quiet equilibrium. It is a future without fire, without fusion, without anything left to burn. The universe is cooling relentlessly, from the incandescent blaze of the Big Bang to the warm glow of star-filled galaxies, down toward a temperature so low that change itself becomes scarce. This ultimate cold has a name: heat death, the moment when energy becomes too thinly spread to do anything meaningful. No heat gradients, no bursts of starbirth, no engines of chemistry, just stillness settled across endless space. To understand why such a fate awaits, we must revisit a quiet law that governs everything: entropy, the measure of disorder, the tendency of systems to spread out energy as widely and evenly as possible. High entropy. The energy of the universe is unfocused, motionless, unavailable. Low entropy. Energy is concentrated, ready to ignite stars, build worlds, and fuel life. Right now, the universe still hosts islands of low entropy, bright suns, living planets, but the tide is rising. Entropy spreads. Each second we breathe brings everything closer to perfect equilibrium, a state of maximum entropy where nothing interesting can happen. Cold is one of entropy's tools, a slow erasure of possibility. Imagine a cup of tea. Left alone, it cools until it matches the temperature of the room. The warmth spreads, and soon the tea cannot cool any further, because nothing is hotter or colder than anything else. The universe is that cup of tea, on a timescale of trillions upon trillions of years, slowly releasing energy into the darkness that surrounds it. The stars are dropping toward equilibrium. But the room, space, is infinitely large. Heat does not return. It simply dissolves into endless night. Right now, stars shine because gravity compresses gas until fusion begins, releasing light and warmth. But hydrogen, the simplest and most abundant fuel, will not last forever. Stars burn it constantly. One day, all usable hydrogen will be locked into collapsed remnants. White dwarfs, neutron stars, black holes, objects that no longer produce new light. Over the next 100 trillion years, the last shining stars will flicker out. Then, darkness becomes dominant. Galaxies will remain, but they will grow cold, quiet, lonely. The universe will transition from the age of starlight into the age of remnants, a slow fade into obscurity. As time marches on, black holes will be the final havens of energy. Their gravity traps motion for eons beyond imagination. Yet, even black holes cannot resist the slow pull of entropy. Through Hawking radiation, they leak energy so slowly that a giant black hole may take 10,000 years to dissolve, a number with more zeros than atoms in the visible universe. When the last black hole sighs out its final whisper of radiation, the deepest cold of all will begin. No more stars, no more collapse, no more gravity-causing change, only scattered particles drifting farther apart in a space too large for any reunion. Time will stretch so thin that nothing noteworthy will occur again. In this state, temperature still technically exists, but only as a ghost. Everything inches toward absolute zero, but never reaches it fully. Residual motion remains because quantum rules insist on it. Particles vibrate faintly, not enough to create, only enough to exist. Entropy will be complete, no region hotter or colder than another. A uniform bath of tiny energies spread across a silent cosmos. The universe becomes a sea of nothing happening. But this destiny is not one of sudden ruin. It is gradual. So slow that human imagination struggles to hold the scale. Our sun is still young, galaxies still form, black holes still grow. There are more bright nights ahead than we could ever count. Heat death is not a threat. It is the natural calm at the end of a very long story. Even so, the thought brings questions that stir the quiet mind. Does meaning survive when motion ends? If no new stars ignite, what becomes of wonder? Does the universe die, or does it simply rest? Perhaps heat death is not an ending, but a transformation, the moment when energy becomes too peaceful to rearrange itself further. Entropy seeks rest. Cold gives it that rest. Some theories suggest that quantum fluctuations may still create brief sparks of structure and heat even in that final darkness. Tiny bursts of ordered energy appearing and disappearing as the vacuum plays its endless game. But these flickers are not stars, not galaxies, not life. They are echoes of a universe that once knew fire. The heat-death horizon reminds us of something profound. Warmth is temporary, light is rare, life is improbable. Yet here we are in the glittering age where stars thrive and worlds can host consciousness. We exist in the universe's moment of celebration, the chapter where motion still matters, where thermodynamics leaves room for curiosity and awe. The cosmos is cooling, but it is not yet cooled. There is still time for love, for discovery, for wonder. Entropy's future casts a quiet perspective on the present. Every sunrise, every burst of lightning, every heartbeat is a temporary victory against the inevitable drift toward stillness. Life is heat arranging itself beautifully for a short time. The universe celebrates our warmth because it cannot keep it. Tonight, as you rest, you can feel this cosmic story woven into your own body. Your warmth, radiating gently into the cool air, is the same warmth that stars shed into the void. Your atoms store the energy of ancient suns. Your breath is motion borrowed from the universe's youth. Time will slow one day, but not tonight. Right now, you are part of a universe still awake, still burning, still full of change. As our journey into cosmic cold continues, a new question rises from the quiet horizon. If the end is stillness, what can the coldest places teach us about the beginning? What secrets of creation lie preserved in the frozen relics of the earliest stars? In the next chapter, we turn back toward discovery, to the places where cold reveals not death, but the origins of everything that ever warmed enough to live. Part 13. When black holes go cold. Black holes, paradoxically, may evaporate through Hawking radiation, releasing their heat into the cosmos until only a whisper of cold mass remains, and even that slips away. Black holes are often imagined as ultimate consumers of heat, cosmic abysses where temperature and light simply end. Yet the truth is more subtle, more haunting. They do not just swallow energy, they also give it back slowly, quietly, until the last warmth they contain is released into the infinite dark. This idea was once inconceivable. A black hole was defined as a region from which nothing, not even light, could escape. It was the final door, a prison of gravity with no exit. Then, Stephen Hawking asked a daring question: what happens at the edge, the event horizon, when quantum particles flicker in and out of existence? The answer changed physics forever. The vacuum of space is not empty. It seethes with temporary particles that appear and vanish in instants. Normally, these particle pairs come and go together, reuniting, canceling, disappearing. But near a black hole's edge, gravity tears pairs apart. One particle falls inward, the other escapes, and that escaping particle carries energy away. We call this slow leakage Hawking radiation. As a black hole emits radiation, it loses mass, a process that grows faster as the black hole becomes smaller. So while the largest black holes take unimaginable times to fade, tiny ones, if they exist, would burst away swiftly in a final brilliant flare of heat. Paradoxically, black holes become hotter as they evaporate. In their last moments, they blaze with furious intensity before silence falls completely. A black hole's life is a journey from unimaginable heat to unimaginable cold, and back to a final surge of fire. At birth, when a star collapses inward, the black hole's core is wildly energetic. It forms from stellar temperatures reaching millions of degrees, compressing matter into a state beyond comprehension. But then, something strange happens. The temperature we feel from outside its horizon depends on the black hole's mass. Massive black holes, like the giants at galactic centers, are colder than the background radiation of the universe. They are so cold that they absorb heat faster than they lose it. They grow by drinking starlight and swallowing matter that wanders too close. Only when the universe outgrows the stars and the darkness deepens will black holes begin their true cooling. Far into the cosmic future, when star formation ceases and galaxies lose their spark, gravitational giants will rule the night. Black holes will drift as caretakers of the last heat, absorbing stray particles, merging into larger and darker forms and locking away energy that has nowhere else to gather. They become the archive of the universe's warmth. And then, the archive begins to leak. As the universe expands and background radiation chills below the temperature of even the largest black holes, energy will stop flowing into them and begin flowing out. Their evaporation is a final release of all they once consumed. Heat returns to darkness. This is not a quick ending. Hawking radiation is delicate beyond imagination. A black hole with the mass of a star could take 1066 years to evaporate. That number is so large we struggle to comprehend it. Longer than galaxies have existed, longer than any current star will shine, longer than the atoms in your body will remain bound. But eventually, evaporation will win. The black hole will shrink, its temperature will rise, its glow will quicken. The final moments may be the brightest thing in a dead universe, a last spark in a cosmos grown silent. Then, the black hole will vanish, leaving only ripples in space-time to remember it ever existed. In that far future, when the cosmic calendar reaches its quietest chapters, black holes will be the last objects to hold structure, heat, and history. Their evaporation marks the end of motion worth the name. Entropy has nearly triumphed. Cold reigns. The heat-death horizon becomes present reality. But one mystery remains. What happens to the information about everything that fell inside? Stars, planets, light, perhaps even civilizations? Does that information simply vanish? For decades, this question shook physics. If information is destroyed, the laws of quantum mechanics break at a black hole's edge. Stephen Hawking originally believed information was lost. Later, evidence suggested otherwise, that information may be encoded somehow in the radiation that escapes. This puzzle, the black hole information paradox, is still unsolved. Whatever answer awaits, it is tied to the same cold fate that evaporates black holes themselves. The quiet future of the universe depends on how black holes whisper their final secrets. In a world where light has faded and heat has scattered, a black hole's slow evaporating glow may be the last trace of active physics. Tiny particles escaping gravity's strongest grasp become the universe's final flicker of change. And when the last black hole dissolves, there will be nothing left to radiate. No more engines, no more exchange, no more transformation. A cosmos of near-zero energy, beyond even the concept of night. A stillness so complete that time itself loses meaning. This cold destiny may seem bleak, an ending without renewal. But perhaps it reveals something beautiful. Everything that warms owes its existence to contrast with the cold. Life needs gradients, stars need fuel, worlds need warmth drifting in a sea of chill. The universe celebrates its pockets of fire precisely because its backdrop is freezing. Black holes going cold are not the villains of nature. They are the last guardians of what once burned brightly. Their end is the universe's sigh of relief after a long, brilliant story. As you lie in stillness tonight, your own warmth radiates outward into the darkness of your room, just as stars radiate into space. Your body, your breath, your heartbeat are part of the same struggle against entropy that drives black holes, supernovae, and galaxies. You are warmth existing in a universe that trends toward cold. You are motion in a cosmos that slowly forgets motion. You are the celebration of energy before its final, gentle rest. As our quiet exploration continues, a new question drifts into view. If black holes cool and vanish, what remains? What structures survive the coldest future imaginable? In the next part, we explore the faintest echoes that may persist when the universe has nearly forgotten heat, ghosts of motion and matter lingering at the edge of absolute silence. Part 14. Could life survive in endless winter? Life depends on motion, on chemistry, on warmth. Yet even in the coldest corners of our solar system, chemical whispers hint that survival might be possible in pockets of hidden heat. On Earth, every living thing is powered by the tiny collisions of molecules, reactions that rely on energy to unfold, remove warmth, and those reactions lose their rhythm. Cells freeze, metabolism pauses, life grows still. But nature is more resilient, more creative than we once believed. And the cosmos knows how to tuck warmth into its cold, deepest places, how to shelter a flicker of motion in environments that should be impossibly silent. The question that emerges is quiet, but profound. Can existence endure in the universe's darkest winter? And if so, what form would it take? Here in our solar system, we already see hints of survival in extreme cold. Not far from the boiling heart of our sun, worlds of endless ice drift in quiet arcs, yet beneath their frozen crusts, oceans move. Europa, Enceladus, and Titan each hide waters deeper than any ocean on Earth. Their surfaces rest below 100 Kelvin, rivaling the coldest natural places in the cosmos. Starlight cannot warm them. Day and night are meaningless in such darkness, and still the seas below remain liquid. Tidal forces, the gravitational tug of giant planets, knead their interiors like soft dough. This motion generates heat deep beneath the ice, fueling hydrothermal vents where minerals bubble up into surrounding waters. On Earth, life thrives in vents just like these 2 kilometers below the ocean's surface. No sunlight at all, only chemistry. Cold above, warmth within, a refuge carved into winter. Extremophiles on Earth, life forms adapted to limits, push our understanding further. Some bacteria remain alive frozen in Antarctic ice for over 100,000 years. They wait for the return of liquid water, their biochemistry slowed to a near standstill without losing its spark. Arctic fish survive sub-zero oceans with natural antifreeze proteins that stop their cells from crystallizing. Microscopic tardigrades endure temperatures near absolute zero by drying themselves into protective glass-like shells, a form of survival called cryptobiosis, where metabolism dips almost to zero. On the edge of cold, life becomes a quiet idea waiting patiently for motion to continue. Cold does not kill, it pauses. Move outward beyond the reach of our sun's warmth, and the cosmos reveals more secrets. In molecular clouds, frigid nurseries colder than 10 Kelvin, complex organic molecules form slowly over centuries. Amino acids, sugars, precursors to proteins and DNA, not life itself, but the alphabet from which life is written. These chemical seeds are preserved in cold until a star ignites and warmth returns the chance to grow. Life's story may begin in deep freeze, long before it awakens to fire. Some scientists believe there could be life 1,000,000 kilometers from any star, tiny organisms powered by chemical gradients, by the energy and radioactive elements within rocks, or by geothermal heat that leaks from the interiors of lonely worlds. Imagine a rogue planet flung from its star, wandering forever in darkness. No sunrise, no day, only an endless icy night. But if it holds a liquid ocean trapped beneath insulating crust and heat trickles upward from a still warm core, then chemistry continues. Molecules collide, reactions persist. Life, sheltered from the cold vacuum above, might adapt to thrive without light. It would not fear winter. Winter would be home. As we look farther in time toward the universe's long cold future, these possibilities become more urgent. They do. When stars fade, their planets may not suddenly die. Oceans could remain under layers of reflective ice for billions of years after the sky goes dark. The last life in the cosmos may not bask in sunlight. It may huddle around vents in a black ocean on a drifting world. Cold forces life to become resourceful, to find warmth in the smallest of places. The laws of thermodynamics suggest that life requires energy flow, a path from hot to cold along which reactions can occur. Even in deep cosmic winter, tiny gradients may persist: heat from radioactive decay, pressure-induced warmth inside thick ice, chemical imbalances waiting to be resolved, rare sparks of cosmic radiation. Life could stretch these meager gifts into survival. It would live slowly, changing with the patience of geology instead of biology. A metabolism measured in millennia. Time in the cold is plentiful. One day, heat death will loom. Stars will have burned their last. Black holes will evaporate into quiet darkness. The cosmos will be a vast ocean hovering just above absolute zero. Could life cling to existence even then? Some theories say yes, in forms that stretch the definition of life beyond biology. Artificial minds powered by faint thermal gradients, quantum systems preserving information in the tiniest shivers of motion, networked organisms of computation dreaming slowly in cold vacuum, waiting for fluctuations in the quantum field. Life may evolve to seek energy in the last places it can be found, not in sunlight, but in cosmic silence, not in chemistry, but in information, a thinking universe refusing to dim completely. If life can exist where heat is scarce, it changes how we see ourselves. We are not an exception. We are one variation in a spectrum of possibilities. Life burning near stars, life simmering within moons, life whispering in the cold, life nearly still but still alive. Warmth makes life vivid, but cold gives it endurance. A frozen organism can wait longer than a burning star can shine. Even here, in your quiet room, the warmth you feel is a fragile moment. Your body weaves chemistry made possible by the sun, but the atoms that make you once wandered in cold darkness for billions of years. You are proof that the universe knows how to store potential in winter. Your warmth is the awakening of ancient frozen memory. So as we set our sights on worlds far from heat, we look not with despair, but with curiosity. Cold does not end life. It challenges it, refines it, prepares it for resilience. Life is motion, and motion can become subtle enough to almost stop without disappearing. As long as a spark remains, cold is not the end, but the long pause before the next fire. And as our journey continues, a final question emerges from the silence. If the universe's coldest places can preserve life's ingredients, can preserve stars in diamond stillness, and can preserve time itself, what are they preserving? 4. What is the purpose of such patient storage in the quiet dark? In the next part, we drift into that question and explore how the coldest places may be less like endings and more like beginnings waiting for their moment to awaken. Part 15. The Beauty of a Universe. That cools cold is not emptiness, it is contrast. It shapes stars, planets, and time itself, a necessary quiet that makes every burst of warmth more miraculous. We often think of cold as a lack, a missing flame, a stolen comfort. But in the cosmic scale, cold is not a thief. It is the environment in which everything meaningful stands out. It is the canvas, and heat is the ink. A star without cold darkness around it would not shine. A planet without winter would not know the cycles that shape life. Even time itself relies on contrast, moments of change and moments of stillness woven together. Cold gives the universe its structure. Heat gives it its story. From the Big Bang onward, the cosmos has been learning how to cool. It began impossibly hot, a boiling sea of particles so energetic that atoms could not form. Only when temperature dropped did the universe begin to organize itself. As the fire faded, electrons settled around nuclei, the first atoms forming in a calm that heat could never allow. Cooling created hydrogen and helium, the seeds of stars. Later, when light finally broke free and the opaque plasma thinned into transparency, the universe entered its childhood. Galaxies bloomed, gravity sculpted, and cold held everything in place long enough for structure to grow. Without cold, there would be no atoms. Without atoms, no stars. Without stars, no worlds. Without worlds, no life. Silence is not the opposite of music. It makes the notes possible. Cold is that silence. When astronomers look into deep space, they are looking back in time. The farther we gaze, the younger and hotter the universe becomes. Galaxies appear crowded, stars forming in furious bursts, chaos everywhere. But closer to home, in the Middle Ages of the cosmos, things move slower. Stars burn more gently. Galaxies stretch apart as space itself expands. Cold has begun to lead. We live in that middle, in the brief era where heat has not yet faded, but cold has gained enough ground to create complexity. We exist in the universe's equilibrium, not too hot, not too cold, just stable enough for awareness to arise. We are children of the cooling. Cold shapes worlds in ways we often overlook. On Earth, ice locks away water for centuries. Seasons regulate migration and growth. Polar regions circulate ocean currents. Winter creates the pause that spring needs. Every living system pulses between warmth and cold. Life breathes in cycles. Heat stirs life into action. Cold grants time for patience, recovery, preparation. Even biological sleep is a kind of cooling, a nightly retreat into stillness that keeps us alive. Cold is the universe teaching rhythm. In the darkness of space, cold does more than sculpt life. It preserves history. Frozen cores of comets store chemistry older than the sun. Crystallized stars hold records of fusion deep within their hardened hearts. Molecular clouds keep ancient ingredients safe until new stars awaken them. Cold remembers what heat would erase. Every frozen grain of dust is a time capsule. Every quiet nebula is a library. We decipher the story of the cosmos because cold wrote the pages carefully and did not let them burn. Even beauty itself deepens in contrast. A sunset glows brighter against the cooling sky. Starlight becomes sharp only against the night. Nebulae shine because the void around them steals heat away, leaving pure light behind. Warmth is spectacle. Cold is perspective. Together, they turn existence into art. Though the future of the universe may appear as a long descent into deep freeze, that fate is not tragic. It is peaceful. Fire flares fast, cold endures. The cosmos would not be magnificent if heat ruled forever. Without cooling, energy would remain concentrated in chaotic bursts, with no time to build the intricate, slow architecture of planets, ecosystems, and consciousness. Cold slows the rush so meaning can take shape. Entropy is not destruction. It is the spreading of potential into every corner of space. When the first stars collapsed and forged heavy elements, carbon, oxygen, and iron, cold carried them outward, allowed them to mix with fresh hydrogen in the quiet darkness between galaxies. Those elements scattered, fell into new clouds, wove new planets, including this one. Your bones contained calcium made in ancient furnaces and cooled into cosmic dust long before Earth formed. Your blood carries iron once fused inside a sun that died before our world existed. You are cooled starlight, stabilized into life. Your warmth is built upon cold's foundation. Even emotions can reflect this cosmic truth. Joy feels brighter against a quiet moment. Connection feels deeper in loneliness's shadow. Rest feels sweeter after effort. We understand meaning because we have known stillness. We value warmth because we feel chill. Cold is contrast in both physics and in the human heart. Tonight, as you lie in bed, you may feel your body cooling slightly, a gentle descent as energy leaves your skin and moves into the air around you. This is not loss, it is balance. It is harmony with the same laws that govern galaxies. Your breath slows, your muscles release, your mind quiets. You enter your own small version of the universe's long cooling, a nightly return to calm and silence. Sleep is the embrace of cold, a reminder that rest is as essential as motion. The coldest places in space teach us that the universe is patient. It does not rush toward endings, it settles into them. It gives time for every atom to find its place, for every possibility to unfold. Cold is not an enemy of life, it is one of its greatest protectors. Because when heat fades, what remains are the structures built carefully in vulnerability, the memories forged while the fire still burned. Cold reveals what truly lasts. So as we conclude this exploration of the universe's frozen wonders, carry this quiet truth. The universe cools because cooling brings order. Cooling brings clarity. Cooling brings peace. If the cosmos remained hot, nothing could hold together. No star could rest. No molecule could endure. No living thing could find comfort. The beauty of cooling is the beauty of continuity, a slow unfolding of creation's patience. We live in a universe that is learning how to rest, and that rest is magnificent. As we transition now toward the final closing thoughts of this journey, let this knowledge curl softly around you. Warmth may flicker, cold may grow, but beauty flows from the contrast between them. You too are shaped by that balance, by motion and stillness, by heat and calm, by the sun above and the quiet night that follows. Now, in the calm that holds you, we drift gently toward the outro, a final reflection on the wonder of a universe that cools itself into peace. Even now, as you rest, the universe continues its quiet journey into cold. Stars breathe out their last warmth. Nebulae drift, letting heat dissolve into darkness. Galaxies stretch farther apart, carrying light into a night that deepens with time. But this cooling is not a tragedy. It is the gentle landing at the end of a long and brilliant story. A story filled with fire and motion, with worlds that awaken and lives that rise to wonder. You are part of that story, a moment of warmth in a universe learning to rest, a rare spark of consciousness woven from atoms that once froze in deep space, then ignited inside stars, then cooled again into the shape of you. Tonight, you carry that warmth forward, a small defiance against the long quiet, a reminder that while cold may rule the vastness, heat makes the moments meaningful. So breathe softly. Let your body settle. Feel the calm of the cosmos mirrored in your own stillness. And if this quiet journey brought you peace, I'm deeply grateful you were here. Your gentle like, your soft tap on subscribe, your presence. They mean more than you know. For now, close your eyes and drift into the quiet, into the stars cooling above you, into the deep and ancient calm that holds every galaxy. The universe is resting, and you can rest with it.